So thanks for the invitation to be here today. I have spoken, let me get rid of this for you, actually. Okay, that's a bit better. Yeah, so I've spoken here once before, but over Zoom, so it's nice to be here in person and to be visiting everybody. So the title of my talk today is, Does Gravity Constrain Complexity? And as with many papers or talk titles that end in a question mark, I'm not going to directly answer the question, and it's going to be a somewhat more speculative talk. But along the way, we're going to hit some concrete results and sort of set up a framework for thinking about this question. Okay. Okay, the clicker issue.
Yeah, there's sometimes I think you need to click on the resume the presentation.
Yeah. Okay, sorry about that. Okay, so starting out very broadly, a question that I'm interested in is how the laws of physics constrain information processing. Okay, so if we think about just quantum mechanics by itself, just the rules of quantum mechanics, then sort of the answer to that question of how those rules affect information processing is the theory of quantum information theory, right? But we know that quantum mechanics is not the full set of laws underlying our universe, right? And there are other constraints on information processing that come from sort of other aspects of physics. So specifically, say from relativity, we know that you can't send information faster than the speed of light. So some additional constraint that at least isn't apparent in the rules of quantum mechanics. And then in quantum gravity, we think that there are additional constraints that are also relevant. So something like, say, the covariant entropy bound. We can interpret this as a constraint on information processing, as a statement that you can't send more than an area's worth of information through some light sheet. So a question that I want to start trying to address today is, if we take sort of the most fundamental description of physics, which we think is some theory of quantum gravity, what then are the consequences for information processing? So if I replace quantum mechanics with quantum gravity, what is the new quantum information theory? Okay. One of the big picture ideas here is that we can start to address this by making use of ADS-CFT. So we can think about information processing tasks that happen in the bulk ADS spacetime, right? And then turn questions about information processing in the presence of gravity into some other question about information processing now without gravity by going to the boundary picture. And then we can make use of our understanding of quantum information theory there to try and address this sort of more fundamental question. Okay. A little bit more specifically, the question about information processing in the presence of gravity that I want to address is the question of if gravity places some sort of constraints on computation. So somewhat more concretely, I want to imagine I have some sort of a space-time region, which I'm drawing as this little diamond here. We have some quantum systems coming in, some quantum systems coming out. That should be an A1, sorry. And we want to know what transformations can relate the inputs and the outputs. Is it just all unitaries, as maybe a naive understanding of quantum mechanics would suggest? Or are there some additional constraints that come in when I'm thinking about this in a gravitating space-time? Okay.
Why not just ask this about the simpler picture where there's only one system and you're asking why unitary is transforming that? Why is it important that there are two?
The way that I'm going to set this problem up, which is going to be an ADS 2+1, there's going to naturally be like two faces. And these two systems are going to come in from infinity, or from spatial infinity. So I'm going to have to, I guess maybe the short answer is like, in order to ask this question in a boundary anchored way, it's going to naturally split the input system into some subsystems.
I mean, I know what kind of experiments you think about.
Yeah, exactly. Yeah.
And why those are interesting. I'm just trying to sort of. Yeah, I was hoping that you could characterize the question you're asking already at this level in a way that made it clear why it's going to be two systems in and out.
That's a good question. I don't think I have the answer. Yeah, but it sort of pops out in the way that I know how to address it, I guess. Yeah. Yeah.
Is your question maybe connected, or can be rephrased as sort of a ADS, flat limit of the ADS scattering
Yeah, I think you could kind of think of this as like a quantum information theorist's version of a scattering experiment.
Right, so would you then say that whatever you find here would also constrain the scattering matrix?
In flat space or in?
Well, the flat limit of the ADS.
Yeah, so I think I'm going to try and come up with some sort of constraints that are phrased in like a computational language, but in principle those should, those are also some sort of constraints on the S matrix. I just wouldn't know how to.
There's no map.
I wouldn't know how to map this into a constraint on the S matrix.
Okay.
Yeah. This is like very different languages and hard to translate. Okay, so yeah, we're going to think about what transformations can happen here in this subregion of our spacetime. And what we're going to argue is that when we phrase that question in the bulk and turn it into a boundary question, this will amount to, or this will be related to a question in quantum information theory about what's called a non-local quantum computation. And in particular, it will be related to the amount of entanglement that you need in this particular information processing task, in this non-local quantum computation. Okay. So we get to turn this question about gravity into a very traditional sort of question in quantum information theory about how much entanglement you need to do some information processing task. Okay.
If you immediately ask, does gravity constrain how much entanglement is required, blah, 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 right? Then it would have been obvious that you need two systems in and out, right? Because otherwise you can't ask questions like that.
Yes. So you could, I think maybe the sort of thing you'd look for is you could just say, I have one input system A, and then I want to try and place constraints on what computations can happen. And then I would look at different ways of splitting A and impose this constraint on all of them. And that would be the sort of full set of constraints on just the problem you're talking about. You could get a constraint in a bunch of different ways.
Where I don't need to, where I'm not imposing some kind of split up, and those are just not the ones that you want to discuss. I mean, that's totally fine, right? But it's not like this class of problems that you're focusing on now is completely universal, right? I mean, I'm not an expert on this, so that's a question.
Yeah.
Is there anything, if you try to break an arbitrary unitary down into 2-qubit gates, are you imagining that each 2-qubit gate is going to be something that's constrained by a setup like this one?
No, it's going to be the full set of gates that's constrained by a setup like this one. Yeah, so I guess, yeah, I think this maybe is a bit restrictive, and I think part of the point is I don't know how to ask the more general question that you're asking for. Yeah.
That's totally fine.
Yeah. Though, yeah, we could revisit this question as well as we go. Okay, good. And then, yeah, the other point I was going to make here is that aside from this gravity motivation, there are just various reasons within quantum information theory or within in cryptography as well to try and understand this question. And so one nice thing is while I won't be able to sort of definitively answer the gravity question, in attempting to do so, we're going to end up with some concrete results just within quantum information theory. Okay, good. Okay, good. So before I jump into what I'm going to discuss, I just want to recall some earlier work that's towards addressing the same question. So this is from Seth Lloyd back in 2000, who argued that gravity would somehow constrain the complexity of transformations that we could do within some subregion. The way that he argued this was he just wanted to take the ordinary rules of quantum mechanics and then add one piece of input in from the gravitational side. So the gravity input was just that the energy of all the stuff you have inside this region should be bounded above by the mass of a black hole that would enclose this region. And he wanted to take that plus quantum mechanics and impose some constraint. It turns out that his argument is very plausible, and I think it's still interesting, but it turns out strictly the way it's stated, it's not correct, it's wrong. And in particular, in 2017, Stephen Jordan constructed an example where he's imposing all of Lloyd's assumptions but showing how you can do an arbitrarily complex unitary. Okay. Jordan's counterexample, is not maybe not realistic. It ignores things like the no signaling principle, or it ignores the covariant entropy bound and things like this. So if we sort of put in all the physics, it's very plausible, I think, that there is some bound on complexity. But this is just to say that this is an open question, and yeah, one of the questions I'm going to try and address. Okay. Good. All right. So the first thing I want to do is explain how we can, in the context of ADS-CFT, translate this question about computation within these subregions into this question about non-local quantum computation. Okay. So the first thing is I'll need to be a little bit careful about what kind of subregions I'm talking about and how they're going to be defined. So I'm always, in this talk, going to be thinking about computations that happen inside of what I'll call a scattering region. So the scattering region is defined by picking 4 points. So these are my C0, C1, R0, and R1. And then intersecting their light cones to form some region. So I'm going to look at the future light cone of C0, future of C1, past of R0, past of R1. Intersect these 4 light cones, you'll get some finite region. Okay. And then I also want to be careful about where the input systems to the computation are going to start and where the outputs are going to end up. Okay. And in particular, we're going to say that these 2 inputs, A0 and A1, are going to start out at C0 and C1. And then after the transformation happens, they should be returned to R0 and to R1. Okay. Good. Yeah. Now, as I said, we're gonna think about this in the ADS context. So our 4 points are going to be at the boundary of my ADS space, right? And then the scattering region will be some subregion in the bulk here. I've drawn it as a point, but in general, it's not a point. It's some extended region. Okay. I'm also going to make use of a sort of schematic picture like this on the right. This is, not really a space-time picture. It's just a circuit picture that captures all of the causal connections in the space-time picture. So yeah, we'll just also use that. And these yellow dots are always going to indicate, sort of some unitary or quantum channel that can happen to the systems that come in.
Alex,
Okay.
sorry if
Yeah.
you said that. So should I think of C0 and C1 like that as just like a local operator in the boundary, or can it be a region as well?
So right now, oops, sorry. Right now they're not operators. They're just like geometric points.
Okay.
They don't actually have to be points. They can be like regions.
Okay.
In this talk, I'm sort of simplifying things by just taking points. But yeah.
You're not allowing J to be a black hole, right?
Yeah, for now, in this talk, I'm not going to be thinking about spacetimes with a black hole. I'm going to say a little bit more later what kind of spacetimes I'm talking about.
But the idea is that we're picking a fixed background and requiring that back reaction should remain small.
We're going to go past that, actually, in this talk. Because I really want to ask, like, what are the actual limits on computation? And in general, your computation could involve, adding so much inputs or so much matter that it's going to change your geometry.
But then I'm confused because the simplest change people would worry about is that they form a black hole.
Okay, that's true. So, okay, I'm going to defer this question for a moment because I'm going to talk about this carefully a little bit later. I think it'll be clearer to just get to it. But yeah, it'll come up again, and if it's not clear, please bug me.
Just a question.
Yeah.
J is defined by causal structure in
Yeah.
in a bulk.
Yes, so it's take the light cones in the bulk geometry, and there'll be this, yeah. Okay. Hugo?
And I was just going to ask, so if it doesn't form a black hole, should I just think this is sort of like some shocks that collide at like not that much energy in center of mass? So is this the type of interaction that you're going to do? Or?
Yeah, we're gonna allow like any interactions, including those that could make black holes.
Okay,
I think I
that's not
misspoke in reference to the earlier question. Yeah. Yeah. In some, I mean, skipping forward slightly. I'm always going to start in a case where like the state on this time slice where C0 and C1 are. This is going to be the CFT vacuum, and then we're going to think about adding sources, like sort of in the immediate future of C0 and C1, which is going to throw in some matter, and beyond that, I don't need to constrain the geometry. So those sources could be such that it builds a black hole in the interior. Yeah. Okay, good. So, okay, some of you will have seen me go through this sequence of slides before, so I apologize, but I just want to make sure everyone's on the same page. So what I want to do next is, there's this kind of a process that we're thinking about in the bulk. So these systems can come in, interact, and then come out again. And I just want to think about what that looks like in the boundary picture. Okay, so the first thing to note is just that, okay, because I put these points at infinity, right, I had the inputs come in from infinity, I can identify these 4 points with points in the boundary. And then whatever quantum information is stored in this system A0 here, because it's coming in from infinity, will be stored near this point C0 in the boundary description. So this means that there's the same in and out states in the bulk picture and in the boundary picture. So the same transformation from psi to u acting on psi will happen here. But it's a little bit perplexing to think about how it happens in the boundary. In particular, while these 4 systems can meet up in the bulk, the geometry in the boundary will be such that there's just no location for them to meet up geometrically. And instead, the process there will have to happen in some sort of delocalized kind of way. So I just want to run through why that's the case and talk about the geometry in the boundary for a second. So here are the future light cones of C0 and C1. Slightly confusing to look at because the sides are identified, but it's OK. Now I've added in the past light cones of R0 and R1, right? And then the point I was making a little bit more precisely is that if I say try and bring A0 and A1 together at a point like this, P0, then system A0 can get out correctly, but A1 will be too late. It won't get there. So that doesn't work. Similarly, I could have tried to bring systems together like this at P1, and then A1 can get out correctly, but now A0 cannot. Okay. So we have nowhere we can locally do the interaction in the boundary. Another way to say this is that the scattering region taken in the bulk geometry, right, taking that intersection of light cones in the bulk, is non-empty, and then the scattering region taken in the boundary geometry is just an empty set. Okay, good. So how should we think about this process as happening in the boundary? Well, in the bulk, everything meets up at these, all 4 lines can meet up. In the boundary, you never have all 4 points meet up, but you can have all the sets of 3 meet up. So how we should think about this process as happening is, we can have some sort of transformation, take the input from C1 and send something towards R0 and send something towards R1, and then some sort of transformation in the future of C0, send something to R0 and to R1. And what's going to have to be true is this process will have to reproduce this interaction. Okay. An important aspect of this is that part of what helps you realize the same transformation in the boundary is that there is entanglement in the boundary, in particular between these 2 diamonds I've drawn in pink here. So those regions are defined like this. I call them V0 and V1. They're boundary regions. They're defined by taking the future of, say, C0 and then the past of R0 and R1, right? That's V0. And then if I look at the future of C1 and the past of R0 and R1, that's V1. There's a bunch of entanglement shared between there, just in the state in the CFT. And we actually know that for certain transformations in the bulk, even certain very simple ones, you actually need entanglement between these things. And so, in previous work with John and Jeff, we talked about how, whenever there's a scattering that can happen like this in the bulk, these regions, V0 and V1, have to share a lot of correlation. Okay. The kind of idea that we're going to think about here, though, is sort of in the other direction. So we're going to say there's some finite, constrained amount of correlation between these regions, V0 and V1. And what that's going to mean is that whatever computations can happen inside of this scattering region, they have to be contained in the set of computations that can happen non-locally using however much correlation there happens to be in the CFT. And so what we want to try and do is constrain this set, right? And thereby constrain the computations that can happen inside the region. Okay, so it's sort of flipping the perspective of this earlier work. Okay, any questions?
Can I think of this
Yeah.
as quantum teleporting part of the input from C0 to C1? Well, I guess you have to teleport it to some place in the future, like these other dots you put in the future, and then you can do the computation there.
So if you,
Is that how you're using
Your
it?
first instinct was right.
yeah, it's, okay, so the ways that we, okay, what I'm going to say today is sort of agnostic to how it actually happens in the boundary. Like the kind of statements we want is whatever you try and do by exploiting this entanglement, there's going to be some constraints, but the procedures that we have for doing these computations in this, like for rewriting this in that form, do involve like exploiting teleportation. And this sort of thing it could look like is you have some system here, then some input system here. You measure as if you were teleporting, such that that system appears over here, but it appears with some poly correction, which you would normally fix up at the end after communicating in teleporting. But now you try and like act on that system plus the system you got here, even with the poly kind of in the way. So you exploit like that first measurement step in the teleportation protocol. Yeah. Yes.
And I can always think of entanglement-assisted communication, computation in that way. Like
We don't know that that's the most general thing you can do.
We
Like,
don't know that.
yeah, that's just like one thing that people have worked out. But
And that is one way to do any unitary you might want to do.
yeah,
Any unitary you might want to do can be done with some generalization of a teleportation protocol.
yeah, it's not a Bell basis teleportation like you would know. It's something called port teleportation. It uses an enormous amount of entanglement, and we think that there should exist better ways to do it. But the general strategy we have uses some.
Uses exponential amounts of entanglement.
Okay, so this is like sort of stated vaguely the kind of way that I want to get a constraint on what can happen inside this bulk region. Next couple slides, I just want to like make this a bit more precise. Okay, so this is the most confusing part of the talk, at least for me to explain. So just bug me until it starts making sense. Okay, so the first thing is we have to be a little bit careful what we actually mean by the scattering region, because like the sort of setup that we have in mind is we have some initial state on this time slice where C0 and C1 are. Then we're going to, inside of these regions V0 and V1, add some sources or couple to an external system such that we add some matter that's going to travel into the scattering region. The scattering region is now this tetrahedron thing. We want to know, by doing that, what computations can I have happen in the bulk? Okay, but the scattering region, when I do that, its actual shape will change, right? So I'm adding some matter, it's going to deform the geometry, and the way that this looks, will change as I do that. So I don't want a notion of the scattering region that's going to depend on what I try and put in there as inputs. So instead, what you should do is you should think of the scattering region as defined just by this data. Okay, so it's just defined by the initial state and then the placement of these 4 points. Yeah, okay. And this data doesn't change when I add these sources, and so this doesn't vary depending on what I throw into the region. Okay, so this is sort of the first point. Yeah. The next point is that, okay, somehow we're expecting this limited amount of correlation in the boundary. Yeah.
So what you're saying is this data doesn't change, but the actual set of bulk points corresponding to it can?
Yeah, so the geometry of this region will change as I vary what sources I add. And so, for instance, as I add more matter, this region could get smaller, but I'm still going to call that the same scattering region because it's defined by this same set of data. Okay. Yeah, so the next thing is, roughly what we want to do is say this limited amount of correlation in the boundary is going to constrain what can happen inside this bulk region. But I would also like to be able to interpret that constraint in bulk language, right? So I want to be able to phrase a constraint that doesn't refer to data about the boundary. And so what that's going to mean is I want to be able to capture how much correlation, say measured by the mutual information, there is between V0 and V1 in terms of some kind of bulk data. And in particular, it'd be nice to have it in terms of bulk data relating to the scattering region itself, so in terms of the geometry of the scattering region. Okay, so that's the next thing I want to do. To do that, I'm going to have to limit the settings that I'm thinking about a bit. In particular, I'm going to have to limit myself to the case where this state on this initial slice that contains C0 and C1 will correspond to the CFT vacuum state. Okay. So that means my scattering regions always have in this first slot just the vacuum. Okay. But then I'm going to add sources in, right? So I'm not just talking about vacuum or like pure ADS geometries. I'm just starting out that way. Okay. Then I can consider turning on different sources. That's going to like change the geometry of this region in the middle. But a geometrical fact is if I turn off all the sources so that I'm just in pure ADS, then the area of the scattering region in that setting fixes the mutual information between V0 and V1. Okay. So this is something that follows from the techniques that we worked out with John and Jeff in this paper I talked about last time I was here. We usually don't mention this when we talk about that paper, but a fact that follows from the techniques there is that half the mutual information between V0 and V1 is equal to the area of this surface along the bottom of the scattering region that we call the ridge, divided by 4g Newton.
So
Yeah.
is the ridge not like R0 then? Like I guess R0 is irrelevant in this slide, right?
Sorry.
You called the ridge R0, but you also called the output point R0.
Oh, shoot. Sorry. Yes. So,
zero here means vacuum.
okay, we're going to call this R0, so that at least when I say it, it will be different. But I apologize that on the slides it looks exactly the same. Yeah. So, or I'll just call it the ridge. But it's in particular the ridge in the case where all the sources are turned off, right? Because when I turn them on, the ridge may get smaller. Yeah, though it is true that this ridge is the biggest one. So when I turn on sources, it will actually always shrink. Okay, so then with these details that I've added in, we can rephrase our constraint in a somewhat more precise way. Okay, so we're going to say the computations that can happen inside of the scattering region, or inside of a scattering region with the undeformed area of A R0, okay, that set of computations has to be contained in this set, which is the set of things that's computable non-locally with a resource system, right, shared between these two input regions that has a mutual information given in terms of the area of that ridge in this way. Okay, so just as a sort of intuitive check, one thing that you see here is that as you make the region bigger, we expect we can kind of do more unitaries inside the region, and as we add more correlation, we expect that we can do more and more computations in this non-local way. Okay, and then somehow these like have to match up. Okay, good.
If you made a black hole, that just means the scattering region vanishes.
I think your scattering region will close before you ever make a black hole.
Yeah.
Yeah. But I'm not putting in by hand that you can't make black holes. I'm just
Yeah.
yeah.
But in the end, you want us to think about all the possible scattering experiments that I could do, including ones which do deform this area.
Yeah. Yeah.
I think actually this is the thing, Alex and I got a little confused about this earlier today, but you probably could do something that, if your scattering region is big enough, you could probably do something that makes a very, very small black hole. And that would still be legal, as long as it's much smaller than the scattering region.
That's
It's not
certainly,
close at all.
yeah, that's right.
Okay. Yeah.
But yeah.
Yeah. The setup is sort of agnostic to this, but
Sorry,
Yeah.
I might be missing something.
yeah.
But I mean, the way that make a black hole.
Well,
I-
what if two people come together and make a really small black hole, and then it's so small that it evaporates almost instantly, and they collect the radiation and they split it up into two systems and they send it out into.
Okay, so I'm allowing that sort of manipulation.
Yeah, maybe that's a good way to do computations. I don't know. Maybe black holes are optimal for some computational thing. I don't, Yeah, Vincent.
Just to double check like the subset is because you expect there are other, like ADS-CFT is just one example of non-local computation. So
Yes.
That applies to subset, but like, would you expect equality? Like.
Oh yeah, yeah. I mean, there could be. This is one constraint on this set, but there could be bulk physics that is not captured by this fact that also constrains computation. So this could be a strict. This could be a strict subset.
Yeah, I guess
yeah.
It would be maybe a little bit more surprising to me to have the equality.
Yeah, I would find inequality surprising.
Yeah.
Yeah. Yeah, because there's no reason that this constraint has to capture, like, this imposed in the boundary has to capture every aspect of bulk physics that might be relevant here. Yeah, but it does. I don't know. We'll get into it, but this does seem to be somehow very constraining. Okay, good. So, okay, the last thing I want to say about sort of the setup here, and kind of the gravity side, is just that there is an assumption underlying this story that I've just told. And in the past, I haven't been super, I always say it's a quantum information argument, not a proof. And the reason I always say argument is this assumption. In the previous story I was telling, like in this paper with John, we have independent ways of proving the same statements, and so I don't worry about this assumption very much. But in this case, I'm not going to have like I won't know how to prove things directly in the bulk, and so I think it's more important to keep this assumption sort of in the back of our mind. I don't think it's super important, but yeah, I should just say what it is. Okay, so I said we should model the process that happens in the boundary with something like this. So there's some operation here, and here, and here, and here. And another way to say this is, in terms of just a sort of causal schematic, it would look like this, right? I've just rearranged these points in a different way here. There is something that this is missing, though, which is that there are these regions between the V0 and V1 diamonds, and there's extra degrees of freedom that like come into these output locations from those regions, right? So a more accurate causal schematic would look like this. Okay. This turns out not to matter at all in the context of proving these theorems that I talked about with John and Jeff, and I think it will continue to not matter in the story I'm telling here, but at this moment I don't have a proof, and if you want to make everything rigorous, you would want to think about this setting, not this one.
The left and right diagrams at the bottom don't look the same.
Left.
Yeah.
Oh yeah, sorry. Yeah, this should go into this. Yeah, that's just an error on my part. Yeah. Okay. Okay, good. Okay, so the first thing I want to do is talk about sort of things that we already understand about these non-local quantum computations and what they seem to teach us about bulk physics. Okay. So I'm going to make a definition. So given some unitary, I'm going to say the minimal mutual information that I need in some resource state to do that unitary non-locally. I'm going to call it E of U. Okay, and E of U is defined with respect to some sort of splitting of the input system into A0 and A1, so I have this subscript here. Okay. The constraint I was talking about earlier tells you that whenever this quantity E of U is bigger than this area, right, then for whatever reason that unitary is just forbidden from happening inside of the scattering region. Okay. In some simple cases that I'm going to go through, we understand some lower bounds on this quantity E of U, right? So if we can use those lower bounds to show that it's bigger than this area, then that's going to be some constraint that needs to have some interpretation in gravity. And so I just want to explain what those bounds are and then explain what they mean in gravity. Okay. So an example of a setting where we know how to prove these bounds is this task that I call the B84 task. I've used it before. The way that it works is we have these four input points, these 4 points, C0, C1, R0, and R1. At C1, the input is a classical bit, Q, which is either 0 or 1. At C0, the input is a qubit, okay? The qubit is in one of these states, HQB. B is also a bit, either 0 or 1, right? H is the Hadamard, which takes 0 to plus and 1 to minus. So if Q is 0, then this is either the 0 or 1 state, depending on B. And if Q is 1, then this is either the plus or minus state, depending on B. And then what you want to do is get B to both R0 and R1. Okay, good? That's the sort of unit task. And then what I want to consider is repeating that n times in parallel. Okay, so now you're going to get a set of n input bits Qi here. I runs 1 to n. Each of those is chosen independently and at random. Then there's a set of n qubits here. They're all in similar states where Bi is also chosen independently and at random. And then what you have to do is get the set of all of the Bi's out to both of the R0 and R1. Okay, this is something we understand pretty well. From a sort of bulk or a local perspective, the way that you would complete this task is you would just bring things together, right? Undo h to the q by knowing q. That means this state will always be 0 or 1, depending on the value of b. So then you just measure in the computational basis, send the measurement outcome to the left and to the right. Okay. You do that in parallel. The important point is you do that in parallel for each qubit. Okay, so if you think of this circuit that completes this, this task as like a depth 1 circuit. Okay. In order to do this non-locally, we know something about this quantity, E of u. We know that it's bigger than some constant times n, where the constant is less than 1. It's about 0.2. And we know that it's less than n. Okay, so if you give me n EPR pairs, so 1 EPR pair for each qubit, there's some procedure that I've illustrated here, but I won't get into the details. It involves a teleportation that lets you do it. And then we also have proofs that this is sort of nearly optimal in that you need a linear number of EPR pairs. Okay. Okay, good. So in this context, we understand the entanglement requirements pretty well. And now I want to understand what this means when I fit this into the constraint that I was talking about earlier. So remember that for this, okay, or I should say, we're going to consider thinking about this. We're going to consider this, this B84 task repeated in parallel, and we're going to try and perform it by using the bulk spacetime. So we're going to send our n qubits of input in, our n bits of input in, and try and get the outputs to both locations. And then what I want to know is, given a particular scattering region, how many times can I do this task? Okay, how many, how big of a depth 1 circuit can I run inside of here? Remember that we had this statement, which is that the mutual information in the boundary is given by this area of the scattering region. And then we also had this statement, which is that the amount of mutual information I needed is at least alpha times n. And then this is the minimal mutual information. This is however much mutual information you have in ADS-CFT. So this is, again, a lower bound. If I stick these two things together, I get this constraint. Okay, so it says I can only do this task at most a number of times that's linear in the area of the region. Okay. This is an interesting looking statement because it's a familiar looking statement. And in particular, we know how to, recover this kind of a constraint from a bulk perspective. So from a bulk perspective, what I would do is I would look at this scattering region. I would think about the ridge along the bottom that I'm calling R here. The faces of this tetrahedron are defined by these future light cones of the 4 points. So they're actually light sheets. And so I can apply this covariant entropy bound and learn that the entropy passing through passing through the region, which here is just equal to the number of qubits, should be bounded above by the area of the ridge R. Okay, so these bounds are the same up to this number alpha. Okay, and then using a slightly smarter task than the one I described, you can get alpha to be as big as a half. So they're sort of the same up to a factor of a half. Okay, so this, yeah, this is very interesting to me. It, you know, it's interesting that we start to recover sort of the one new thing about constraints on information processing in the bulk that, you know, that we think we know. So to me, that sort of is a good indicator that we're kind of on the right track for recovering constraints in the bulk. It's also intriguing in that, you know, maybe this hints at sort of the physics underlying the covariant entropy bound, right? This gives some sort of mechanism where a constraint like that arises. Of course, the statement I can get here is much more limited than the covariant entropy bound. It only applies when I started out with the vacuum here, and then for these ridges that are constructed by intersecting light cones in a particular way. So it's a very special case, but it's interesting that you get something like this. Okay.
Can you say what alpha is?
What's that?
What alpha is?
Yeah, so numerically for this task, alpha is 0.22 roughly. For a smarter task, I can make it as big as a half. The family of tasks for which I know how to prove bounds, you know that like the best I could ever possibly prove will be alpha like less than or equal to 1. So that's kind of intriguing. I don't know if they're like the best one I could pick in that family gave me a half, but it's also clear that like you'll never get bigger than 1, which is kind of an interesting numerical thing, but yeah.
And you're working in units where 4G H bar is equal to 1?
4G H bar, I set H bar to 1, but G Newton is,
Can you go back to the next? Sorry, you've got the 4G.
yeah. But H bar is 1, yeah.
I think there was a previous slide where 4G disappeared.
Oh, it's, yeah. Okay, that is possible. Yeah. Okay. Yeah, any questions about this? This is one of the more concrete things I have to say. So. Okay.
When you actually think about doing this, I mean, so in the bulk, you're literally doing this diagram where you simply bring the classical bits that carry the Q together with the quantum bits.
Yeah.
Right? And you just sort of do this. But, you know, in practice, long before you start saturating the covariant bound, you actually make a black hole, right? You can't actually bring an area's worth of matter into a region like this.
Right, yeah, so that may be reflecting the fact that like this constraint I'm giving is, you know, presumably not an equality, so it's just, yeah, like this may not be tight, right? Like, there's nothing in my argument that says this is tight. It's just saying n has to be less than this area.
Yeah, I wonder whether there is some way to make it. I mean, you would probably have to make black holes in special states that evaporate very quickly or something, but
To saturate it, you mean?
Yeah.
Like how would you imagine saturating it in the
Yeah.
bulk? Yeah, I have little intuition there.
Even going to the order A, you probably have to black hole, right? You won't be able to do that.
Like as soon as you're on the order of the area, you mean?
yeah, linear scaling with A is hard.
Yeah, yeah, right. Yeah. Yeah. Okay, yeah, so yeah, there may be tighter constraints, but this is what you get from this. Okay, so good. So now, like, what I want to go to now is thinking about trying to do unitaries in the bulk that would be more interesting or more complicated. So the thing that completes the task I was just describing in the bulk is this like depth 1 circuit. And there it looks like the constraint that you get is just a constraint on, you know, how much stuff you can pack into the region. But I'm also interested in, are there additional constraints that come from, not just trying to fit the stuff into the region, but what I actually try and do inside the region. So that constrains like the process inside of the scattering region. Okay. So for a general unitary, the thing that we know about this entanglement cost is that it is upper bounded by an exponential in n. Okay, and this comes from this port teleportation protocol that was mentioned briefly earlier. So given this and given this story I've been presenting, there are two possibilities that could be true here. The first is that the only constraint in the bulk is the covariant entropy bound. And so what that would correspond to is that like the only, if the only constraint in the bulk is the covariant entropy bound, then it would require that the entanglement cost here is always just linear, right? Because if you can prove a stronger bound than linear, then that's going to scale in a stronger way than the covariant entropy bound, and so something more has to be true. The other possibility, right, so either this is just always linear or it's not, and gravity imposes some additional constraints that come from, not just what you fit into the region, but what you do inside of the region. Okay, so I want to explore like which of these do I think is true, and if there are further constraints, what should they look like? Okay. My suggestion is that it's the possibility B that's true here, and that gravity is constraining some appropriate version of the complexity of what I'm doing in the bulk. Okay, and yeah, the rest of the talk I'm going to try and like motivate that statement. Okay. So the first thing we need to do to make this proposal a bit more precise is to clarify what version of the complexity we're actually talking about here. And there's an apparent obstruction to saying it should be the complexity that controls the entanglement cost, which is just that for a unitary like this one, which is product across this split A0 and A1, this could have large complexity, but it's clear that this will have zero entanglement costs just because you can just do this locally on both sides without exploiting any entanglement or even communication. Okay, so to account for this, we have to define an appropriate notion of complexity, which is what I call the interaction class complexity. So we first of all have to define the interaction class. We'll say that two unitaries, u and u prime, are in the same interaction class if they're equal up to these like local unitaries on each side. Okay, so if you can relate u and u prime by some set of these four operations, v left, v right, w left, w right, then we say they're in the same class. Okay. Then we're going to define a complexity, which is the interaction class complexity, which is just like the complexity of u minimized, or the interaction complexity of u is the complexity of it's the minimum complexity of all the unitaries in its interaction class. Yeah, it's a bit of a tongue twister. Okay. So you can kind of, what this means is, I give you u, and you can like freely try and simplify u by adding in these processes on each side, and it's just the complexity of what you're left over with that we're going to count. Okay.
Are they like v's and w's fixed at first, or do you optimize over?
You optimize over those, yeah.
Okay, over those
yeah.
as well.
Yeah. So you're trying to like take out as much complexity by acting on each side. In a bulk perspective, this would correspond to like, we don't really know how to constrain exactly what happens inside the scattering region. All we know how to constrain is like what goes in and what comes out. And so this is corresponding to the fact that as things fall in, you have a long amount of time to like do whatever process, and then you try and simplify what you actually have to do inside of the region. Yeah.
And then the actual like complexity you're using is just like the local.
Yeah. So okay. So I'm slightly agnostic to that. I think it should be something like the circuit complexity. But most of the tests I have aren't really sensitive to which. So you could define an interaction class complexity for whatever measure of complexity you want to stick here. Concretely, for this talk, let's have in mind the circuit complexity with like a order 1 local set of gates. Yeah, and then the proposal is that this entanglement cost should be some sort of polynomial function in this interaction class complexity. Okay.
I'm a little confused why there's not a U prime on the right-hand side.
Yeah, this should be prime and this should be prime. Yeah. Thank you. Okay. Good. So, okay, let's just do some like basic sanity checks here. The first sanity check is that if I have U and U prime in the same interaction class, then they will have the same interaction class complexity, right? Just from the definitions. And they will also actually have the same entanglement cost, just because if I have some protocol that does one of them non-locally, I can, using a certain amount of entanglement, I can add onto that protocol unitaries locally on each side at the beginning and the end to make a protocol to do the other one, and vice versa. So they have to have the same cost. So okay, that checks out. The second thing is that the upper bounds we have on these quantities are the same. So we know the maximal, or the upper bound on the amount of entanglement that I need to do some unitary non-locally is like 2 to the order n, where n is the number of qubits in the unitary. And similarly, the naive upper bound on the interaction class complexity is also 2 to the order n. Okay, so this looks good. At least at like very high complexities or entanglement costs, they seem to agree. And then the other sanity check is for really simple unitaries, say depth 1 unitaries, the interaction class complexity will be order n, and the entanglement cost will also be order n. Okay. So yeah, it has the basic properties that you need. Good. To explore this proposal in more depth, we can try and simplify the problem. So the problem of like very generally understanding, give me a unitary, what is the entanglement cost to implement that unitary? I think this is a very hard problem. This is something that people in cryptography have thought about a lot, and I think getting a full and explicit answer to that is probably for now out of reach. But we can try and simplify the problem in different ways and see if the simplified problems are consistent with this proposal, at least as a check. So there's 2 ways to simplify things. The first is we can restrict the strategies that we're going to use. So in particular, what we can say is instead of doing arbitrary unitaries on each side, acting on some entanglement, and then doing arbitrary unitaries on each side, we can say, let's restrict the set of unitaries we're going to use, and for example, let's just use Clifford unitaries. Okay. Cliffords are very tractable. We have more tools there, so maybe we can make some headway. And indeed, it turns out that within that sort of restrictive Clifford world, the proposal is just true. So the entanglement cost to implement some Clifford using only Cliffords is equal up to order 1 constants to this interaction class complexity. Okay, so the proposal holds in that space. The second thing you can try and do is you can focus focus on specific tasks. So instead of giving you a general unitary, I can give you something with more structure. And in that context, you can try and look for better upper and lower bounds. And then what we're going to do later is we can also pick 2 different tasks that have a lot of structure and compare the complexity entanglement relationships that they show. And according to this proposal, that should always be the same, whatever task I choose, or whatever class of tasks I choose. And so it's seeing whether that holds or not is some test of this proposal. Okay. Good. Yeah. How am I on time? I lost. Okay, like 5 minutes or something.
Yeah, you can pass a little.
Yeah. Okay. Okay. So I'm not going to show the result for Clifford's. It's fairly straightforward. I could talk about it, but I'm going to focus on this second strategy of restricting the class of tasks and comparing across tasks. Okay, first, yeah. So we're going to compare 2 things. The first thing I want to talk about is the task of implementing a Clifford unitary. So I already mentioned this a bit. There, we know that the entanglement cost is just linear in the input size to the Clifford. And you can also characterize the complexity of Clifford unitaries. And it turns out to be captured, the complexity of a Clifford turns out to be captured by this complexity class called mod KL, okay? I'm not gonna define that. You can define that class like in terms of Turing machines and all of this. I'm not gonna get into that. What you should think of mod KL as is it's the class of problems that you can solve by looking at your problem, choosing a Clifford circuit, running your Clifford circuit, and measuring one qubit of output from that circuit, and using that to decide the problem. Okay. Something you do need to know about the class, though, is that it sits between log space and poly time. Okay, so solving problems in that way is more restrictive than having a polynomial time Turing machine, and it's less restrictive than having a Turing machine that uses only logarithmic memory. Okay, so it's somewhere between there. And we think both of those are strict. So we think it's strictly bigger than L and strictly smaller than P. Okay. Good. So according to the proposal, since we see that here using polynomial, or specifically linear entanglement, you can do everything in this class mod KL, it should be the case if I pick some other problem that I can also do everything with complexity in mod KL using polynomial entanglement. Okay, so we want to put that to the test. The other task that I'm going to pick is what's called F routing. So here, the task involves a classical string of length n, which I'll call x, input on the left, and then a classical string of length n called y on the right, and then also a quantum system of some order 1 size, so just order 1 qubits called q on the left. Okay. And then the task, or what you need to do, is to bring the system q to the side labeled by some function of x and y. So each task has an associated function, f. I have to compute f and then bring q to the side labeled by f. Okay. This is probably the best studied task in the cryptography literature because it happens to be really favorable for the cryptographic scenarios that they're thinking about. Yeah, so that's just a comment. Okay. So the best strategy that the cryptographers have come up with is what's known as the garden hose strategy. The number of EPR pairs you need, there scales like an exponential in the memory needed to compute f on a Turing machine. Okay, so 2 to the memory compute is the entanglement cost. It's already sort of interesting, I think, that you see the complexity coming up here. Like the complexity is telling you an entanglement cost already, at least within this set of protocols. So that's kind of nice. But what you can observe is that if you restrict to having polynomial entanglement, then that restricts you to having logarithmic memory. So the set of things that they can do efficiently with this strategy is restricted to L, log space, which comparing to the Cliffords is apparently too small. So according to our proposal, we should be able to do better than this. Okay. I'm going to skip this because I'm a little short on time. So we think that we can do better. And we think we should at least be able to do mod KL. It turns out that there is a strategy for doing better, and this is work that I did with Sam Cree, who's a graduate student with Patrick at Stanford. The basic strategy is to exploit quantum error correction. Okay, so the idea here is, or let's go through a really simple example. So say that the function we want to do this task for is just the AND function. So x and y are single bits. And then we're going to take x and y, and we want to bring q to the side that's labeled by x and y. The way that we're going to do this is we're going to take q and put it into an error correcting code with 3 shares that corrects 1 erasure error. Okay. Then what we do is we take the first share and we just always keep it on the left. Okay. Regardless of what the inputs are, we always keep it on the left. So I'm going to summarize what we do with each share in this table. So regardless of the inputs, we see that S1 is just always on the left. Okay. S2, we do something slightly more interesting. We look at the value of x. If it's 0, we keep S2 on the left. If it's 1, we send it to the right. Okay. S3, we do something a little more interesting, which is we measure it in the Bell basis with this EPR pair so that it's appeared up to a polycorrection on the right. Then that quantum system, the other end of the EPR pair, we bring to the side labeled by Y, right? So overall, we want to get S3 to the side labeled by Y, but it's slightly troubling because S3 starts out on the left and Y starts out on the right. So to get around that, you need this one EPR pair. Okay. So in the table, we see that, yeah, S3 when Y is 0 ends up on the left, and when S3 when Y is 1 ends up on the right. Okay. Then you can see that this does the task for you because this table here corresponds to like the truth table for the AND function. So in these first 3 cases, right, the AND function is 0. And indeed, we see that there are 2 shares, which is sufficient to get Q on the left. And then in the case where the AND function is 1, there's 2 shares on the right. And so you end up with it on the right side. This is a sort of detailed example, but the general strategy is you're trying to construct an error-correcting code whose what's called its access structure, so like the pattern of subsets that recovers Q and the pattern that the set that doesn't, matches the structure in the function you're trying to do this task for. Okay. So you can generalize in that way. You just sort of go to the literature, you look for an appropriate class of error-correcting codes. The best thing you can find is this construction due to Adam Smith back in 2000. And there, what you can achieve is that the entanglement cost for doing this routing task on the function f is upper bounded by what's called the span program size of f. So span programs are some model of computation, and their size is some measure of their complexity. And so this, yeah, span program size is just a measure of how complex the function f is. Then what's really nice is that the class of functions with poly-size span programs, which here is the class of functions we can do with poly entanglement, happens to be exactly this class mod KL. Okay. So that brings us into alignment with the expectation from this proposal, and thereby gives some evidence for this proposal. And another nice thing is that because mod KL is a bigger class than L, this is now the most efficient attack on these cryptographic schemes that people talk about. Okay. So it's kind of nice that we started out thinking about quantum gravity, but now we can just say something nice about these cryptographic schemes. Okay. So yeah, that's all of the content I wanted to say. A couple of summary comments. So we wanted to think about information processing in the context of quantum gravity. The general strategy is let's use ADS-CFT to turn questions there into questions about quantum information without gravity. More specifically, we thought about computations in a gravitating region and how those are related to non-local quantum computation. And then still more precisely, we said computation in a scattering region with some particular area is contained in the set of non-local computations with using a mutual information that's fixed by the area of that region. Okay, and then we had this sort of dichotomy of either you can do way better in non-local computation than we think we can do on the quantum information side, or there's some constraints on computation in the presence of gravity that go beyond the CEB. And in particular, we had this proposal, so we thought it was the second thing, and we had this proposal, which passed some sanity checks, turns out to be true for Clifford-only protocols, implied some implication about being able to do better in this particular F-routing task, which then turned out to be true, so that's nice. So these things all support the proposal. And then if the proposal is true, somehow gravity is constraining the complexity of what happens in the region. Okay, so that's everything. Thank you.
So questions for audience? I'll start with a quick one. So
Yeah.
in Seth Lloyd's case, he had
Yeah.
sort of like a simple idea of like, oh, it's constrained by like the mass of the black hole or something
Yeah.
like that. Do you think that something could be?
Yeah, so there should be some bulk mechanism. I haven't really tried to think about what the bulk mechanism would be. I mean, in the really simple case where I know what the bound is, and we get this linear bound for these like depth 1 circuits, then the mechanism seems to be the CEB, right, which is strong enough to imply the entanglement-based constraint. But beyond that, yeah, I haven't, yeah. but you're like, there should be some picture.
Any other questions for Alex? Yeah, if not, let's thank Alex again.